Hi everyone, welcome back to Food for Thought Physics, where today we're going to be analyzing a special type of 2D motion known as projectile motion. Projectile motion deals with the motion of an object when fired at some velocity and some angle relative to the Earth's surface. Here we're going to use our x-axis as representing a line across the surface of the Earth that the projectile flies across, while the y-axis is going to be the altitude above the Earth at any given point of the projectile. So you might be thinking, wait, that doesn't seem right. After all, we know the Earth isn't flat, so why are we using this flat x-axis to represent the surface of the Earth? Well, while it is true that the Earth isn't flat, it is also true that along short enough distances, the Earth does seem relatively flat. And so we can use this flat x-axis as an approximation for the surface of the Earth across short distances. That simplifies the math considerably. So let's consider a projectile fired at some velocity relative to the Earth's surface. We're going to call this velocity v0 and put a vector hat on it. We'll denote the magnitude of this vector as just v0 without the vector hat, and we're going to assume it's fired at some angle theta above the surface of the Earth. So now what we can do is we can break up this problem into x and y components and then solve each one individually, which we can do because due to the fact that we're putting our coordinate axes as perpendicular to each other, these axes will not affect each other. So let's start with x. First we can find the x component of velocity, which I'm going to put in green over here. And we're going to say that v0 x equals v0 cosine theta, as we learned before in resolving vectors. So now we have this initial velocity for this x direction. And there should be nothing speeding up this object or slowing it down in the x direction, so there shouldn't be any acceleration. So that means in the x direction, the projectile is moving with constant velocity. If we remember what we learned in 1D kinematics, we might see, well, constant velocity means that x is just going to equal the initial velocity, which is going to be v0 cosine theta, times the time, t, plus x0, the original x position. Next, let's look at the y direction. So we can draw this y vector here, the initial y velocity, and we're going to write this as v0 y. And this v0 y is going to equal v0 sine theta. As again, by trigonometry and vector resolution, we have this. And well, what else happens in the y direction? Well, you might remember that gravity acts downwards in the y direction at some negative g, where g is going to be approximately, and this is going to be approximately negative 9.8 meters per second squared. So that's an acceleration. Gravity is going to act downwards with a constant acceleration on this object. And so that means that in the y direction, the object moves with constant acceleration. So we can remember our constant acceleration equation and just say, well, y equals negative g over 2, so half the acceleration, times t squared, plus the initial velocity, which is going to be v0 sine theta, times t, and finally plus the initial y0. So now we have these two equations that describe the position of the object at any given point while in projectile motion. And well, what do we notice about these equations? Well, we see this x here is going to be linear with respect to t. It's going to be some constant times t plus another constant, while y seems to be quadratic in t, some constant times t squared plus some constant times t plus some constant. So that means that we can also theoretically express y as some quadratic of x. And if you know some algebra, you might know, well, what sort of shape does this create? Well, that creates a parabola. So that means that on this xy plane, this object is going to follow an approximately parabolic path. So it's going to be a parabola here. And what else? The other thing we can do is we can find the range of this projectile, the horizontal range, rather. So for now, here we see we have these x0 and y0 terms. So we're assuming that this doesn't start at the origin, maybe. But let's first assume for a second that these terms don't exist, that we're putting the starting point at the origin, And let's also assume that when firing this projectile, it's going to land on the ground, and the ground is going to be the same altitude as the initial starting point. So we're not firing it off a cliff or something. So that means that this is just going to look like this. Theoretically, it could also go further if we started, say, above, or maybe it would be cut off short if we started below the ending point. But let's for now assume that we're going to fire and it's going to land at the same altitude as the beginning. And so how can we find the horizontal range of such a projectile? Well, let's look at this equation first. Assuming that we start at y0, we're going to have that y equals negative g over 2 t squared plus v naught sine theta t plus 0. So we're going to ignore that term right now. And well, when does this projectile land? Well, this projectile lands when this y equals 0. So I'm going to replace this y with a 0 right here. And we're going to solve for t. Well, we can move this g over 2 over, and then divide both sides by t, then divide both sides by g over 2. And then we're going to have that t actually equals 2 v naught sine theta over g. But it takes this long for our projectile to get back to this initial altitude of 0. And now how much has this projectile traveled along the x direction in this amount of time? We're going to call that the horizontal range of this projectile. It's how much it's traveled while in the air for this amount of time in the x direction, because we care about how far, let's say, this projectile travels. Well, here we can just plug this equation into here, or plug this t into here, and we get that this h, which is our final x, equals, let's see, v naught cosine theta times t, which is we're going to replace with this t here, this 2 v naught sine theta over g. And here we can use a special trigonometric identity, which you might know, which is just that 2 times cosine theta times sine theta equals sine of 2 theta. So we're going to substitute that into here. This 2 times cosine theta times sine theta, we're going to transform that into this sine of 2 theta, and we get that, and we can combine these v naughts here, and we get that the horizontal range of this object is going to be v naught squared over g times sine of 2 theta. So our equations are going to be, this is our y equation, this is our x equation here, and this is the horizontal range equation over here. And so, well, let's look at something for a second. We might be wondering, well, does gravity always act with constant acceleration? You might notice that some objects do seem to fall slower than others. Why is that? Well, that's just because of air resistance. Air resistance is just the natural tendency of the air to resist stuff falling down it. So here we're going to ignore air resistance, we see. But does air resistance have an effect? Yes. If there were no air, then the acceleration due to gravity should be this 9.8 meters per second squared downwards. And in most cases, for most objects, air resistance is so small that it doesn't really matter that much, and we can use this 9.8 meters per second squared as a nice approximation. Now, for objects with a very large surface area, or very light objects, say like pieces of paper, you might notice fall rather slowly because the air kind of pushes it around, then this is not true. But for most objects that we usually deal with that we throw, say balls, or some other things that we might throw, then this model here is a good enough approximation. So we have our y position function here, our x position function here, and the horizontal range of the object here. So in the next video, we're going to examine another type of special 2D motion known as uniform circular motion.